5, like one of these sheets or...
There are some, I didn't bring them tonight because I forgot. So, there are some parts of part 1 and part 2, and I'll just make them optional.
So we don't have to,
So you don't have to do,
right, for all 5?
right, for all 5, there's only 2, there's actually 3 parts to 5, and we're only going to do part 1 and 2. We're not going to do, like, I just think that's so interesting, but that's like 64 slides. So part 1 and part 2 homework for unit 5, we're going to make it extra credits. Okay? And I'll bring the sheet for unit 5 homework Wednesday. But it won't count against you if you don't do it. But it will count for you if you do it. I have some people that are turning in their old homework, which is kind of fun. It's a good way to review.
What? Did you say you like drop the grades or like the lowest grades at the very end?
So the way it works like is in the homework, I think I said I was going to drop like 10% of the homework.
Okay.
And then for your unit exams, the way that goes is a lot of times people can hopefully do real well on the final, and so the percentage you earn on the final will count, if it's in your favor, it will count for your lowest units exam, but it will also count as your final.
Okay.
And I think that's kind of what I do. But I do drop 10% of the homework. So, we have 2 quizzes left. Some semesters I just totally blow off. But this semester we're going to get 2 more quizzes in. And actually the quiz at the end of today is going to be basically a question that you're going to see on your final. So what the heck? Okay. And then we'll do another quiz Wednesday. So it's cool, but you guys always come anyway, so you might as well come Wednesday. Okay, so we'll do a quiz then. And any questions about only the first 2 parts of Unit 5. And even though there is homework, I'll bring it home on the sheet Wednesday. You don't have to do the homework, but you can do it. Okay. All right. So the third item now, I've enjoyed reading your lab write-ups. There's a few labs maybe still out there. It gets a little tricky. I think I mentioned this. If you went to a lab that I hosted, you don't have to show me a photo. Okay? If you went to a lab that I hosted. And if you just want to tell me about the lab, I'll negotiate something, but you really probably should type something up. You'll get some points if you tell me about it, but you get more points if you type it up. Okay? So don't make me hunt you down. Any questions about the labs? The labs were due Friday, but you can still turn them in definitely for credit. And definitely any credit's better than a 0. In fact, I think what I'm going to do, and I didn't do it yet, but for the labs that are missing, I think I'm going to put 0s in there so we all know we're on the same page. So if I was going to say, if I were to die today, then you'd know that those were 0s and you need to go ahead and get those cleaned up before the end of the semester. Things wrap up for this class on Friday because I figure you're taking your final Friday, so any work you want to turn in, remember if you're going to try to turn in old homework, you need to do it before you can take your test. That's the only thing that makes sense. So don't go try to take your test at your final and then go home and try to use homework. Because that's it for taking stuff. Okay? So, yep. Cool. The Geminid meteor shower, remember that's, if you're hardcore, you're probably going to want to go like midnight on Wednesday or maybe 11 p.m. on Wednesday into Thursday morning. And look for Castor and Pollux, which is the heads and the twins of the Gemini, constellation Gemini. So we'll see. It's looking like it might be cloudy. All right. So one of the sheets I gave you was, I think I have one left, said something about what you can expect on your final. So it's kind of broken up into sections. First off, remember you can bring a 5x8. Card instead of 4x6. And then I mentioned the 2 parts. And actually, if you kind of go down here under the contents of the final exam, you'll see what you can expect for Unit 5. Now, some of you guys have watched or watched a little bit of my video already. I have the review video out there where I go over every exam, but it goes pretty fast, I think. It doesn't take too long. Yeah. And so wherever there's an X, that question won't make it. So after the X's finally settle, you can kind of see down here the 3 sections on your final. Of course, we have multiple choice, vocab, and short answer. You can see there'll be 50 questions multiple choice, and you actually see where they're coming from. So 12 of them each from the, 12 from Unit 1, 2, and 3, 10 from Unit 4, and 4 from Unit 5. Okay. And then also on this sheet, I went ahead and gave you the review sheet for Unit 5. I'll make it a little review video. It should not hopefully take very long at all. Okay, well, let's see what the last few things I get to stuff into your heads is. Okay, this is actually a topic we've talked about dark matter. When we talked about galaxies, you guys told me that dark matter is mostly located in the halos of our galaxy and other galaxies. Okay, so one of the things, and we'll kind of dive into what do scientists think dark matter is, and they fall into 2 categories. Yes, it is let's see, put on the sheet. I love these terms. It is the machos and the wimps. That's what's going to actually be dark matter as far as what scientists think. But the other thing we need to talk about, or by the way, dark matter, how do we know it's there? Well, you can't see it, but it actually gives a gravitational tug, okay? In the case of how, this is going to be the center of our galaxy, in the case of how stars orbit the center of our galaxy, you told me that stars out here, they go a lot faster than they really should. Okay, the reason that they do that is because there's actually dark matter, stuff we can't see in the halo region of our galaxy and other galaxies too. So the other thing we need to talk about in this unit is dark energy. On the next slide, I'm going to actually, I like what OpenStax has done. I'm going to show you kind of the evolution of, did we always think there was dark energy? No, but I'm going to try to convince you, and I've got a few videos to help me out, that what dark energy is. Because as it turns out, now when I look at this, I think of, starts letter E, who came up with, oh my goodness, we don't have any black here? Yeah. Who came up with E is equal to mc squared? Einstein, yep. So in math, if you have an equal sign, you know that this quantity, which is energy, is related to this quantity, mass. Energy and mass. They're what we call interchangeable. Now, it's a tricky thing to do that, but it actually happens in nuclear reactors all the time. They take a little bit of matter, it's consumed, okay, during nuclear fission or fusion, and it's converted into energy. That's what our sun's doing. Well, if you look holistically at our universe, the contents of the universe, and we break it down into these 2 components, energy and matter, okay, it's got to fall into one of those 2 categories. Well, as it turns out, 68% of our universe is dark energy. Now, dark, don't think it's a bad thing, but it's an important thing. Dark as in not evil, but dark as in important. 27% is dark matter. And then you get down to this sliver right here. Okay, we got 5% is ordinary matter, and of that 5%, 0.5% is the matter that's tied up in stars. So I just think that is so cool. Let's take a look at the first of a few videos I want to show you today, called Accelerate. Actually is a figure from OpenStax, and it's very similar to what you saw a minute ago. It's interesting how things haven't changed much in, probably the previous figure might be 5 years old, and this is probably, OpenStax is pretty current. So again, a large part of what's in our universe is dark energy. So, and then we have this dark matter. We'll talk a little more about dark matter. It's easy for me to talk about dark matter than it is dark energy, and then ordinary matter, 5%. So what does ordinary matter look like? Well, it looks like atoms. But of course, atoms are different types of elements. And the simplest element is hydrogen, followed by helium. So actually, of that ordinary matter, it's 5%, 4% is hydrogen and helium. And I don't know about you, but I got a lot more elements other than hydrogen and helium in my body. I doubt if I have any helium atoms at all in my body. Not a hydrogen, but carbon, nitrogen, phosphorus. So we're going to talk more about dark matter coming up. I don't know if you can tell this, but does this look like gravitational lensing, or this actually gravitational lensing? But this is actually, it's a cluster of galaxies. It's a cluster of galaxies. And we'll talk a little bit about dark energy. So I thought this was interesting. In 1970, we didn't have this idea of dark energy, okay? In 1980, we kind of said, instead of 80s, in general, scientists said that dark matter is probably not ordinary. It's probably got some sort of exotic component to it. In fact, particle physicists have been in the news in the last 2 years or so. The whole God particle thing, I think that was related to hopefully finding some sort of, it's called a subatomic particle, like a particle of an atom, that might kind of be somewhere in the ballpark of giving some light onto what dark matter is. But in here, we're to the point where we kind of have, instead of all of this dark matter, we now know that related to the expansion we observe, there's dark energy, a lot of dark energy in our universe. So I've got another little video to show you. This is like a review slide a little bit. This is looking at different orbital curves. An orbital curve is just like, in this case, it's a merry-go-round. This says, like, if you're sitting in the middle of the merry-go-round, you don't go very fast. But if you're in the edge of the merry-go-round, that's where you get sick, right? Okay, you're going very fast. This is another orbital pattern that we see. This, of course, you recognize the planets. And you guys told me that Jupiter goes more slowly in its orbit than Venus, and then it slows down Saturn, Uranus, Neptune. And that's actually what Kepler observed, and Newton's laws also say that too. And actually this rotational curve, put all these up here, this rotational curve, each of these dots then are stars orbiting the center of our galaxy. And this is, we talked a lot about this in Unit 4. Remember, we should expect that the stars that are farther from our center go slower and slower, but they don't. And again, that goes back to actually there being a lot of dark matter in our halo region. So when we look at other galaxies, this might be a galaxy that we're seeing kind of not face on, but a little bit edge on. We've been talking a lot about the Doppler effect. So what do you think? This A is moving toward, or this location over here moving towards us, so what shift should we see? A blue? Yeah, I agree. What about the location B, where there's no motion? No Doppler shift. Okay, dead on. What about these stars over here in location C, moving away from us? Red shift. So actually we see this in other galaxies, or I should say, we can use the Doppler shift in other galaxies to understand how the stars in the other galaxies are rotating. Okay, so you might recognize NGC is kind of like the Messier Object Catalog, New General Catalog. These are different galaxies, and you kind of see instead of the farther away the star is, it doesn't go slower and slower from its galactic nucleus, or its rotation doesn't slow down, it keeps up. So this actually says in other galaxies, they also have a halo region with dark matter in it. Oops. I don't know if did I check? Let me check out this video right quick. We're in its halo region. Most galaxies have dark matter in their halo region. And then actually, it gets even a little more interesting. Let's kind of pull this all together. When we watch the dance, well, there's a few ways, but if you picture a galaxy cluster, so galaxy here, like a family of galaxies, a galaxy cluster, actually there is dark matter kind of strewn, it's throughout that cluster of galaxies. So there's also dark matter there. And you're like, well, how do we know that? Okay, because there's no rotation or anything like that. We need to observe. Well, I'm going to actually, and did this make it to your test? Nope.
Yes, okay. This slide, you want to put a little star on it if you have your slides? This actually is the second item in Unit 5, Part 1. Okay, so how do we know that there's dark matter kind of strewn between the galaxies in a galaxy cluster? Well, one is to watch the dance. Watch the dance, okay? Basically, we see those galaxies in a cluster of galaxies sort of kind of coming together, moving, okay? And we can understand relative to their mass and how they're moving, what sort of mass must be in between them, okay? So we watch the dance. Another way, and this actually kind of blows my mind, is we can look at a cluster of galaxies and we can understand the temperature of that cluster of galaxies. And from that temperature, we can understand that there is mass that we can't see. It's called dark matter, dark mass, dark matter, okay? From the temperature of the galaxy cluster. And then this last one is something we already talked about. This was on your Unit 4 exam. Gravitational lensing. So remember how gravitational lensing works, and it's kind of vivid in my mind. One of the slides we kept seeing for Unit 4 was that Abel cluster of galaxies. And remember that the way it worked was we saw an older galaxy, or a younger galaxy, a farther away galaxy, and more of a baby galaxy beyond it, that actually the light kind of got bent by the cluster of galaxies. And how much it's bent, that gives us an indication of what sort of mass you're dealing with there. And it kind of goes back to maybe a little bit what the video said, or the videos have said, is that if you know there's mass, and if you can't account for all the mass with the visible stuff you see, then that mass is dark matter. Now here in a minute we're going to say, well, some of that dark matter could be black holes, and you're totally right. But black holes and really dense objects can't account for all of the matter that is there, that we see in the halo region or in the cluster of galaxies. So this is kind of showing you gravitational lensing. Looks like here we are here. This is your cluster of galaxies. This is a more distant galaxy, more of a baby galaxy, and we kind of see remember it looks like guts? It looks like roadkill? Yeah. So there's gravitational lensing. Roadkill. The little blue dashes. Well, there's a lot of things in science, astronomy included, you're kind of like, really? And I usually qualify, my classes are more like survey classes, so a lot of times I'll touch on the highlights of the discipline, physical science. So if you really want to know more, you're probably going to have to get a PhD in it or something, or go and get a BS in it or something. But is it reasonable to introduce something called dark matter? So our dark matter relies a lot on the influence of gravity, okay? So there actually are some two options still here. It could be that gravity isn't what we thought it was, or that, how do I say this? I think it's over here. Either we are truly observing gravitational effects, or there's something wrong with our understanding of gravity. Is there something wrong with our understanding of gravity? And good, bad, or otherwise, there are some things in life that you know are going to be, death and taxes, okay? And honestly, in the physical science world, gravity is one thing that we know a lot about, or scientists know a lot about. So that's probably not possible. So we are observing something have a gravitational effect on matter that we see, but we can't see the thing creating the gravitational effect. And that makes it dark matter. So pretty solid about this idea of dark matter. This is an OpenStax figure, very cute. I think it was a NASA thing. I'm telling you, scientists, So a little box of, looks like cereal, dark matter, new and improved, mystery flavor, nutritional facts, dunno, ingredients, no one really knows. If you figure it out, let us know. Okay. Central relativity, or general relativity up here. That's the people who made it. Dark matter. So this actually gets to another thing that's on your review sheet. So if you want to put a star on this slide too, you can. So the two possibilities, and if you're a Star Trek fan, you've probably heard the word baryonic matter. I know I have. I don't know if it's Star Trek or probably more like Star Trek than Star Wars, but anytime you hear the word baryonic matter, that just means normal atoms, okay? So it's possible and most likely that some of that stuff is just normal matter. It's not glowing, okay? We talked about some things in here that wouldn't glow. A brown dwarf would probably glow, a failed star, depending upon that glow wouldn't reach us anyway, it'd be diluted, okay? So they're collectively called machos. And if you want to, on my note card anyway, I would probably write down what the M, the A, the C, the H, and the O stands for. Macho stands for massive, where'd it go? Massive, compact, halo objects. Now each one of those should kind of, or some of those should ring a bell. Massive means it has a lot of mass. Compact means it's very dense. Halo, what's a halo? Around the outside of the disk. Halo region of a galaxy, objects. Machos. Macho. So the other possibility for dark matter are this. I just think the contrast is cute, right? So machos, it's WIMPs. And in WIMPs, the W, the I, the M, the P, and the S all stand for something. I guess not the S, but what they stand for is weakly interactive massive particles. Weakly interactive massive particles, WIMPs. So dark matter. And honestly, like I think I might have said, machos, sure. Massively compact halo objects that are underluminous. That's definitely some dark matter, but it can't be all the dark matter. It just can't. The math doesn't work. So what WIMPs are is kind of goes back to maybe the God particle. Okay, weakly interactive massive particles. They have mass, but they don't interact with matter, which makes them very hard to find and isolate. And okay, weakly interactive massive particles. Very interesting study. Okay, so what this says is basically probably what we're seeing doing the gravitational lensing, that dark matter that's kind of strewn between the galaxies in a galaxy cluster, it's probably a combination of machos and WIMPs. Okay, so, all right. On Wednesday, we're going to talk more about the beginning of our universe. Okay, and like one of the videos we saw said, I don't know if it used the term singularity, but basically I like the Minute for Physics video we watched because basically all of the matter and energy that's part of our universe was all squished together a long time ago, about 3.7 billion years ago. And as they call it the Big Bang, but as it began unfolding, it created, as it is currently still unfolding, it creates the fabric of space and time that we've been talking about with Einstein. Okay? So it's a temporal, time, and a spatial thing. It is so cool. But anyway, these little, you can't see it very good, but almost these are kind of arrows. It looks like one of those things where you have a magnet and you have the little filings and you make little pictures out of the person's face. Yeah. But these, if you can see them more closely, are actually showing you the trajectories of galaxies as they are moving. And as it turns out, starts letter V, what do we say kind of galaxies are around these areas that don't have anything called voids, exactly. And I don't know if you can kind of start to make out a void here. Okay. Maybe some voids over here. So those are galaxies moving. If you can see it close, you see a little trajectory. These little yellow dots are galaxies also. So this is a look at, we are here kind of the distribution of galaxies going farther and farther from us. So these are galaxies, and you can kind of maybe get a sense for the void regions. But actually, at the time that our universe began, dark matter is a factor. Dark matter is a player. Dark matter is a player. Dark energy is a player. And again, the dark, it's like, it almost sounds like evil, but it's not. Okay? It's a player. From left to right, these boxes, and I think we kind of looked at a little bit of these boxes before. The little blue dots here, this would be like today. The little blue dots would be galaxies, kind of the webbing of our universe, kind of sheets around void areas. So going back in time, this is what our universe used to look like. These aren't drawn to scale. Notice that this, for instance, might be, the cube is 13 million light years, 35 million light years, 70, 93, 140. So the fabric of the space is expanding. Oops, let's have a bunch of builds. Okay, I think this might be about the last slide before our quiz. So I've got 4 different options of our universe. This is universe, not galaxy, not star, not planet. This is options for our universe. The way you read this is we are here, right here, okay? And this would be going back in time. This would be like the Big Bang, okay? This first one, notice what it has, and actually, when I first started being interested in cosmology or astronomy, this was a prevalent still thought, and then evidence has said that it's not the case. But can you see where, what's it going to do up here? What's it look like it's going to do in the future? What's that look like? Does it look like it's coming together? Yep, that would be a now that's the universe, not just a galaxy. Okay, so that would be our universe recollapsing. Okay. There was evidence, okay? And what you're seeing, think of these that I'm going to show you. Think of the blue lines here as the edges of our universe. So we said our universe is expanding, okay, but according to this model, and we don't have the right recipe for this model to be the correct one. Let's look at this one. Okay, Big Bang. Okay, the fabric of space and time expanding. We are here, okay? Notice that this one actually just kind of, instead of getting larger and larger and larger, looks like it's going to kind of just bottom out, right? That's not it either. But in these 2 scenarios, can you see where in this scenario, the time between now and the Big Bang is greater than the time between now and the Big Bang? Well, here's a coasting version. What's the difference between this second version and the third version? It keeps getting bigger and bigger, yep. Now, one of the things we talked about way back in Unit 1 was this: if you're driving 60 miles per hour, okay, you're driving 60 miles per hour, 60 miles per hour, okay, that's not accelerating, right? What if you drive 60, then 90, then 120, and then 150? You're going faster and faster and faster. And so actually the difference between 3 and 4 is 3 is expanding, but 4 is the expansion is accelerating. So instead of kind of like this flat thing, you get, I think it's called asymptotic, or I don't know, some sort of exponential sort of curve. Okay, like that. So this actually is, and I've got a little bit to kind of show you to back this up, but this is actually what we observe in the matter in our universe, the 4th scenario. Okay, so our enlarging is accelerating. So what would you say? Would you say this was the oldest time of the 4? And you know, the way you get to here, going back in time, is to understand kind of where we are or where we're headed and kind of go back. It's called extrapolation. All right. All right, busy. We saw 4 scenarios on the previous one. Those 4 scenarios are reflected here. And I don't know, it kind of confuses me when I look into it. But these scenarios have to do with critical, or the amount of dark energy and dark matter that our universe must have. So for instance, this is the way it goes. We saw that recollapsing one, that was scenario 1. Okay, scenario 1 says that it get bigger and then again it's going to come together. Scenario 2 looked like this, right there. Scenario 3 looks like this. Scenario 4 is that top line. But it has to do with what our universe is made of. Scenario 4 is the real deal. So this one, I don't know if it rings any bells. If you look at the kind of the before and after, the bottom, the top, the bottom, the top, the bottom, the top, the bottom, the top. The thing that's different in the top one, what a rush if you're an astronomer to see this. But actually you have one of the special supernova type 1A events where a white dwarf comes out of retirement because it got dumped on by its companion, exceeds the Chandrasekhar limit and blows up. You can only do it once, but it's got that standard brightness that we're looking for. So actually we can use these as candles to understand how far away they are and then get a sense for what sort of redshift we see in them. So these little dots here, you might recognize I think this is missing a scenario. This is scenario 1, scenario 2, and I know this is scenario 4, okay? I guess the blue one was one of the 4 scenarios. So these little dots actually are the supernova events. And they lie most on a curve that represents the 4th scenario, the accelerating universe. I did have one more. So this is curve number 4, okay? You can kind of see our universe getting bigger and bigger and bigger at an accelerated rate. If you read the caption, actually it says this acceleration didn't kind of kick in until after the galaxies had already kind of moved a little bit away from each other. And we'll talk about that a little bit on Wednesday. So sometimes this, by the way, is called and I don't know, this might be controversial in astrophysics, the world of astrophysics, but the big chill. Because honestly, if the fabric of space and time is getting more spacious, okay, that means at some point, for instance, the atoms that are binding together here, there will be more and more space between them, okay, and sometimes called the Great Rip, okay. The reason it's called Great Chill is that as the matter gets farther from each other, things cool down. So today's quiz looks like this. So take out a piece of paper. Hopefully you have a piece of paper. I was looking for paper. You can even take like an old homework and write on it or something. But somehow, and make sure your name's on it. And you can Google the answer, you can ask your friend, you can look back in your notes, you remember how this works. I haven't done very many quizzes. And we'll do another quiz on Wednesday.